In this video, we'll introduce the chain rule for functions of several variables, well, functions of two variables, but generalizing to more variables is straightforward. So let's just consider a function of two variables where for the chain rule to be applicable, what we have to assume is each of the two variables x and y themselves depend on an independent variable, which we'll call t. So imagine this function depending on x and y themselves are functions of a new variable t. So think of, just to give you an example, let's say that f of x and y is x squared times y plus 3xy to the 4, but x and y depend on a third variable t. X is the sine of 2t and y is the cosine of t. So that's the dependence of x and y on t. Okay, so if you would substitute for x sine 2t and for y cosine of t, you would get a function of t, a function of a single variable t. So this is our composite function, and we want to talk about or compute its derivative with respect to that variable t. Okay, so we could do what I just said, substitute in the function for x and y the corresponding functions of t, and then differentiate with respect to t. But the chain rule helps us, if we don't want to do that, we want to go straight to computing the t derivative without substitution. So let's see how that works. Well, for that we have to imagine what a small change in the function's arguments does to the function. So this connects to the linear approximation and the tangent plane approximation that we've seen before. So a small nudge in the arguments of a function of two variables will give us roughly the partial derivative with respect to x times a small change in x plus the partial derivative with respect to y times a small change in y. And then there are further terms which can be denoted as epsilon 1 times delta x and epsilon 2 times delta y, in which these terms actually go to 0 as delta x and delta y go to 0 respectively. Okay, so this is the compare this to the tangent plane approximation that we had earlier. So once we have this approximation to the change in the value of the function, we can look at the ratio or the fraction delta f over delta t, and that will roughly give us the partial derivative with respect to x times dx over dt plus the partial derivative with respect to y times dy over dt plus epsilon times dx over dt plus epsilon 1 and plus epsilon 2 times dy over dt. Okay, and now if we take this delta t to 0 in the limit when delta t goes to 0, what we get is actually the derivative of our function with respect to the variable t. Okay, in the first term we have the partial derivative with respect to x multiplied by the derivative of x with respect to t. Remember, x is a function of t, so this ratio will converge to the derivative as delta t goes to 0. The second term is similar, but x is being replaced by y, so the partial derivative with respect to y times the derivative of y with respect to t, then what we would have is these extra terms, but in the limit, these epsilon 1 and epsilon 2's, they go to 0. These delta x over delta t and delta y over delta t, they go to these derivatives, of course, but the coefficients of these go to 0. That's why we don't see those terms appear. And this is what we see right here is the chain rule, is the way we can compute the derivative of a function that we obtain by the composition of x with of f with x and y themselves being functions. So let's go back to this example, and I'll ask you to compute with that function its derivative with respect to t at t equals 0. Okay, so I want you to compute using the chain rule this derivative given at t equals 0. Okay, pause the video and input your answer below. Okay, I hope you paused it. So if you want to first compute this derivative with respect to t, what you can do is apply the chain rule and take the partial derivative with respect to x times dx over dt, so the derivative of x with respect to t, and the partial derivative with respect to y is being added to it, which is multiplied also by the derivative of y with respect to t. Okay, let's compute these ingredients. So the partial derivative with respect to x of this function, here you have x squared, here you have x, so indeed this is 2x times y plus 3y to the 4, and the partial derivative with respect to y is, well, here you have y and here you have y to the 4, so it's going to be x squared plus 12x times y cubed. And now we can look at these functions. Well, of course we have x and y as functions of t, so we can indeed already compute these derivatives right here. Dx over dt is going to give you twice the cosine of 2t, while dy over dt is going to give us minus sine of t. So this is just differentiating these single variable functions, so one variable functions. So these are dx over dt and dy over dt, these terms. So all we have to do now is evaluate at t equals 0. So when we do that, okay, remember y of t is, x of t is 2 t, the sine of 2t. So when t is equal to 0, the sine of 0 is giving us 0. So y x at 0 is 0, y at 0 is the cosine of 0, which is 1. So these we have. Then these derivatives at 0, what are they giving us? So at t equals 0, so the x derivative, the derivative of x at 0 gives us 2, and the derivative of y at t equals 0 will give us 0, because of the sine of 0 is what we are having. Okay, so now we know what x, y, derivative of x and the derivative of y are in this formula. So all we have to do is just use the chain rule and input these ingredients with the corresponding x and y values. So we have 2 times 0 times 1 plus 3 times 1 to the 4, and this is multiplied by the derivative of t, or the derivative of x, which is 2, and to this is added the y derivative at x equals 0, y equals 1, so that's 0 squared plus 12 times 0 times 1 cubed, and this is multiplied by the value of the derivative of y, which is 0. So all we have here, if you look carefully, is only this term that remains, giving us 6. I hope you enjoyed this video, and I'll see you in the next one.